Welcome all. Today we are going to discuss a design problem on singly reinforced beam. A rectangular reinforced concrete beam under moderate exposure condition is simply supported on two masonry walls 300 mm thick and 7 meter apart, center to center. The beam has to carry, in addition to its own weight, a distributed live load of 20 kN per meter and a dead load of 15 kN per meter. Design the beam section for maximum moment at midspan. Assume Fe415 steel and M25 concrete. Firstly, we have given the center to center distance between the supports and the width of support is given as 300 mm. From this data, we can compute the clear span as the 7 meter minus 0.15 meter from here and 0.15 meter from here, or in effective it is 7 minus zero point 0.3, that is 6.7 meter. We have given the following details. We can find the clear cover as 30 mm from the given data exposure condition moderate. It is given in IS 456 page 47. There is a table 16. We have the exposure condition and the nominal concrete cover in mm. So, if it is mild steel, we will be providing, if it is mild exposure condition, we will be providing 20 mm clear cover or nominal cover. We have provided with moderate exposure condition. So, we will be taking 30 mm for this current problem. We will be proceeding with 30 mm. The other data we have provided are the grade of steel, grade of concrete, and also the dead load and live loads. The design problem we will be solving in 6 steps. The first step, it is trial section and effective span. Firstly, we assume a breadth. Here we will be assuming it as 350 mm, and the total depth. There is a difference between total depth and effective depth. Total depth is the depth from here to here, whereas the effective depth is the depth here from here to the center of the uh, steel provided. So for a simply supported beam, total depth can be computed as span by 10, or here the total span L, it is 7000 mm by 10 equal to 700 mm. So if the total depth is 700 mm, we will be assuming the effective depth as 650 mm. D dash will be approximately equal to 50. We will be taking the effective depth as 650 mm initially. Now, to calculate the effective span, it is the primary aim of this step, that is effective span equal to center to center distance between the supports, or clear span plus D, whichever is lesser. It is specified in the IS code clause 22.2 page 34. Here center to center distance between the supports is given as 7 meter, and clear span plus D. Clear span is 6.7 we calculated, plus D, which is 0.65 meter. It is we get 7.35. Out of this, the smaller one is this. So we will be taking the effective span, or L, equal to 7 meter. Now the first step is come over. This is the IS page which shows the effective span, that is shall be taken as clear span plus the effective depth of slab or beam, or center to center of supports, whichever is less. The same thing we have explained. Now the second step, loads and moment. Here we will be calculating the factored load and the factored moment. Factored load, or WU, is equal to gamma, or the partial safety factor, into the total load. Total load can be calculated as self weight plus dead load plus live load in the current problem. The current problem includes self weight. So we will be getting the value of gamma, this partial safety factor. We can obtain it from table 18, page 68, IS 456. In the table 18, we will be getting different load combinations. Here we will be having dead load plus live load. So we will be using 1.5 as the partial safety factor for loads. We will be taking gamma F, or gamma equal to 1.5. We will be calculating the self weight as, this is the unit weight of concrete. 25 is the unit weight of concrete. We will be taking for RCC as 25 kilonewton per meter cube, and unit weight for PCC we usually take as 24 kilonewton per meter cube. Then this is the small b and this is the capital D. That is the breadth and depth of the section we are using. That is 0.35 into 0.7. So we will be getting the self weight. Then this is the dead load and live load. So this is the total loads we have, and we will be multiplying these complete things by the partial safety factor, which is obtained from table 18 in the IS 456. We will be getting a value 61.6875. Then we need to go for factored moment, for which we are designing the structure MU. It can be calculated for a simply supported beam as WU into L square divided by 8. We have the value 61.6875 into L, we have 7 square divided by 8. We will be getting 377.84 kilonewton meter. Now the third step, we need to fix up BD and capital D. We know for Fe415 steel, MU limb divided by BD square equal to R limb equal to 0.138 FCK. We should remember these things. It is better to remember this for all, for Fe415, Fe250 and Fe500. So for Fe415 steel, this is the relation. FCK is the characteristic compressive strength of concrete. For M25, it will be 25 Newton per mm square. So the value of MU limb divided by BD square, or R limb, is equal to 0.138 into 25. That is equal to 3.45. Now we need to determine the minimum effective depth for the section. We can calculate it from D is equal to MU divided by R limb dot B, which is the root of MU divided by R limb into B. We get 377.84 into 10 raised to 6, because the bottom B is in mm, so we should convert this kilonewton meter to Newton mm for the correct unit in both numerator and denominator. So we will be getting 559.38 mm as the minimum effective depth. So we will be providing a value which is higher than this. We have already checked that the D value will be some approximately equal to 50 mm. So we will be considering it too. So 559 or 560 plus that 50 will approximately go around 600 and something. So we will be taking the total depth as 650 mm, from which if we subtract the D dash, it will be around 600 mm. So it is larger than the required minimum effective depth. So we will be adopting the total depth as 650 mm. Now, if we adopt total depth d equal to 650 mm, we should revise the effective depth d. For that, we will be assuming there is an 8 mm stirrups which is used to bound these hanger bars around the hanger bars and the main steel bars, and the diameter of the main steel bar as 25 mm. So the effective depth can be found as the from the total depth we will be reducing or subtracting the clear cover. We have it as 30 mm, then minus stirrup diameter. We will be assuming the stirrup diameter as 8 mm, and also we will be subtracting main bar diameter by 2. Here we will be assuming the main bar as 25 mm. So we get the values, the total depth D 650 minus clear cover 30 for the moderate exposure condition, minus 8 as stirrup diameter, minus 25 by 2, which is the main bar diameter by 2. We will be getting 599.5 mm, which is approximately equal to or taken as 600 mm. Now we need to check the d dash value. D dash means the distance for it includes the distance clear cover plus the stirrup diameter plus main bar diameter by 2. It is 30 plus 8 plus 25 by 2, it is 50.5 mm. So from these all things we will be getting we will be fixing up B, D and D. This is small b, small b, small d and capital D. After fixing small b, small d and capital D, we will be going to fix the area of, or we will be determining the area of steel required. For that we will be finding a term mu divided by bd square. This mu is the factored moment we have already find, that is 377.84 into 10 raised to 6, which is used to clear up these units in either sides, divided by 350 into 600 square. This is d, it is taken as 600 now, into 600 square. It will be giving 3 Newton per mm square. And for FE415 and M25, from the design aids, using the design aids or the SP16 data book, we will be going to the SP16 page number, this page with the table 3. In table 3 we can see that it is for Fy for 1 F5 Fy equal to 415 and FCK equal to 25. We will be going to this page. It is in table 3, flexure reinforcement percentage PT for singly reinforced sections. From this we need to calculate PT. We need to calculate PT. These all values are PT values, and what is in this left sides here and here, this is mu divided by bd square, and these values are Fy. We have Fy given as 415 and mu by bd square we have mu divided by bd square, we have already find it as 3 Newton per mm square. So we will be checking where is this mu by bd square 3 and Fy 415. Here mu by bd square is 3 here, and by going to the intersection of these two, Fe 415 and mu by bd square 3, we will be getting a value 0.997. That is, these all are the values of PT. It is given here PT, reinforcement percentage So we will be getting PT as 0.997. It is, remember that it is in table 3 SP16. It will be changing according to the grade of steel and concrete we are using. All this can be found from here. If the grade changes, the page also changes. Depending upon different grades of steel, these values changes. Now, if we can find get PT, it is easy to calculate AST required. It is equal to PT by 100 into BD. That is 0.997 divided by 100 into 350 into 600 equal to 2093.7 mm square. So this is the area of steel required. Only this much steel is required. For the detailing purpose, we need to check that we will be providing some area of steel, but it should be checked that this provided steel should be greater than the required AST. This is the first thing we need to check, and the second thing is that the provided AST should be in between minimum AST and maximum AST. We can calculate this as we can calculate it later. Firstly, to estimate how much number of steel bars we required, we will be doing this. That is, area of one steel bar. We will be calculating the area of a single steel bar. It is AST, small AST equal to pi by 4 into d square. D square is the diameter of the main bar, that is equal to 25. We will be getting 490. So one steel bar is 490.87 mm square area. To find number of steel bars required and AST provided, we will be doing this calculation. That is, the required AST is the AST required is divided by area of a steel. So we will be getting 2093.7 divided by 490, that is equal to 4.26. If we are 4.26 is not a whole number, we can't provide steel bars as 4.26. We can only provide either 4 or 5. So we will be preferring 5. We will be providing 5 steel bars. So we provide 5 numbers, 25 5 diameter steel bars. So the total area of steel provided, the tension steel provided, can be calculated as pi by 4 into 25 square into 5 numbers. We will be getting 2454.36 mm square. Now the first condition is okay. That is, AST provided is greater than AST required. AST required is 2093 something, and we will be providing 2454, which is greater than AST required. So the first condition is okay here. But we need to check that AST provided is between AST minimum and AST maximum. So we need to calculate what is AST minimum and AST maximum. To calculate AST minimum or the minimum reinforcement, you can use the equation AST minimum divided by BD equal to 0.85 divided by Fy. We will be getting the answer as 430.12 mm square. So the minimum reinforcement or the minimum AST should be 430.12. So it is greater, this our value what we got is greater than the minimum required, so it is okay. But we need to check for maximum also. Maximum AST maximum is calculated as 4 percentage of BD or area, that is of gross area. Here it is 0.04 into small b into capital T, that is the exact gross area, that is equal to 0.04 into 350 into D equal to 650. we'll be getting 9100. It is too much higher than 2454 that we have provided. So the our value is AST provided, which is 2454 something, is between AST minimum, which is for some 490 something we have already done here, 430 something, and AST maximum, that is 9100. It is in between. So the second condition for the reinforcement is also okay. This is these two steps to find the minimum and maximum reinforcement is not a must thing in this design process, but it is preferred. So that is okay. uh, Now we are providing the steel bars. We have said that we will be providing 5 number of steel bars. These are hanger bars. This is the stirrup 8 mm. This is the total depth 650 mm, and this is the effective depth 600 mm, and this is the D dash. D dash includes the clear cover plus stirrup diameter plus the distance to main bar by 2, that is 50.5, as we have already calculated. Now we need to check this is design in the output of the design is this, that is how much number of AST bars is required, what is the diameter of that thing, what is the clear cover, what is the effective depth, what is the total depth, and what is the breadth. All these we have find out, but this we have assumed it as 350 mm. So the design process is completed, but we need to check for the strength in its flexure in bending. For that, the factored moment should be greater than the ultimate resisting moment. We have already found mu as 377.84 kilonewton meter, and the ultimate resisting moment mur can be calculated using the formula 0.87 Fy AST into T minus 0.42 XU. Here Fy is known, AST provided is using here, it is also known, D is known, but XU is unknown here. We need to find XU. To find XU, we will be using XU equal to 0.87 Fy into AST. You will be using provided divided by 0.36 FCK into B. We will be getting an answer to 81.34 mm. We will be substituting this to here. We will be getting 0.87 into Fi 415 into AST 2454.6 into D 600 minus 0.42 into XU 281.34. We will be getting the value as 427018729.5 Newton mm. But we need to mention MUR in kilonewton meter. So we will be converting the unit, that is 427 kilonewton meter. This is the MUR. It is less 427 and MU is 377. So surely MU less than MUR. MU less than MUR. So it is safe. Now we need to check for the deflection control too. To calculate the different deflection, we will be first calculating the percentage till or PT provided, that is 100 into ST provided by BD. We will be getting a value 1.1688. Then we will be finding Fs 0.58 into Fy into AST required divided by AST provided. It is equal to 0.58 into 415 into 2093 AST required into AST provided 2454.6. We will be getting a value 205.31. After that, we will be going to our IS code in figure 4 and figure 5 to get a modification factor in tension and compression. So this is the figure 4. We have the equation F is equal to 0.58 into Fy into AST required by AST provided here. Here we will be getting the value PT provided as 1.1688 and Fs as 205.31. Now closely examining this graph, you can see that Fs values are denoted here as the curves. F is equal to 120, F is equal to 145, F is equal to 190, and such way. Our obtained value is F is equal to 205. That is, it is in between 190 and 240. So there is a curve this way in between. Also, we have the value of PT provided as 1.1688. 1.168 is less than 1.2. It is come around here. We will be drawing a imaginary line in our mind. It will be passing through this position, and 205 will be coming through here, and it will be meeting somewhere here. So we will be checking what is the modification factor here. This is 0.8, this is 1, this is 1.2, and this is in between. So we'll take the modification factor as, or the KT modification factor in tension as 1.1. Once more explaining, here we will be getting 1.1688. Here is 1.8, 1.2. Here is 1. 1.16 comes somewhat here. It will be drawing an imaginary line in our mind. The Fs is 205. It will be coinciding here, and we will be collecting this point, that is 1.1, as the modification factor KT. Similarly, we will be looking for modification for the compression reinforcement. Here we are not using any compression reinforcement, so the percentage steel will be 0. It is 0%. So the modification factor, or Kc, corresponding to 0% steel is 1. So Kc is taken as 1. Or note that for the singly reinforced beam, modification factor will be taken as 1. For the singly reinforced beams, the modification factor in compression reinforcement, or Kc, is taken as 1. So Kt is 1.1, the modification factor in tension, and Kc equal to 1, the modification factor in compression. Since Pt equal to 0, or we can say that no compression reinforcement, so Kc equal to 1. To check the deflection control is our aim. So we will be checking this data. L by D provided should be less than L by D maximum. So firstly we will calculate L by D maximum. This L by D basic can be calculated, can be seen from the IS code. That is, it is 20 for simply supported, 7 for cantilever, 26 for continuous beams. Here it is a simply supported beam, so L by D basic will be 20. We have find KT and KC, substitute those values, we will be getting 22. Now we need to check what the value of L by D provided. The effective length is 7000 mm and the effective depth is 600 mm. The ratio is 11.6. So surely we can say that 11.6 is less than 22, or L by D provided is less than L by D maximum. So the structure is safe. So this completes all the steps of the problem. Hope you have understand. Go once more through the problems. It will surely help you to master all these programs, these problems. Thank you.